In a generator, the conductor rotates uniformly in a magnetic field. Because of this continuous rotation, the flux linked with the conductor also changes continuously at every angle of rotation. This is why the induced voltage follows the pattern of a sine wave. Let's understand the journey of conductor inside a generator. Let's look at the 0-degree position. When the conductor moves to the 0-degree position, its motion becomes parallel to the magnetic field lines. At this position, there is 0-degree angle between the motion of the conductor and the direction of the magnetic field lines. Because no flux lines are being cut, the induced voltage, that is, the generated voltage, is equal to 0. It matches the sine function. Because sine 0 degree is equal to 0. As the conductor moves to the 45-degree position, its motion now forms a 45-degree angle with the magnetic field lines. Here, the conductor cuts through some of the flux lines, which results in a moderate voltage. This voltage is about 70% of the maximum value. And this matches the sine function. Because sine 45 degrees equals 0.707. Next, at the 90-degree position, the conductor's motion becomes perpendicular to the magnetic field lines. This is where the maximum number of flux lines are cut. As a result, the conductor generates the maximum positive voltage. And mathematically, this matches the sine function. Because sine 90 degrees equals to 1. Which is the maximum value of sine function. When the conductor reaches 135 degrees, the voltage decreases back down to about 70% of the maximum. And this matches the sine function. Because sine 135 degrees is also 0.707. Now, at the 180-degree position, the conductor is once again parallel to the magnetic field lines. And it cuts no flux lines. So the generated voltage is 0. And sine 180 degree is also 0. As the conductor moves further to 225 degrees, the situation looks just like what we saw earlier at 45 degrees. But in the opposite direction. Now the conductor cuts the flux lines at a 45-degree angle. But this time the induced voltage flows in the reverse direction. Its value is about 70% of the maximum. But negative. And this fits perfectly with the sine function. Because sine of 225 degrees equals minus 0.707. Similarly, the 270-degree position is the mirror of 90 degrees. But in the opposite direction. Here, the conductor moves across the magnetic field lines from left to right, cutting the maximum number of flux lines in reverse. This produces the maximum negative voltage. Just as sine 270 degrees equals minus 1. Next, at 315 degrees. The situation mirrors what we saw at 135 degrees. Again in the opposite direction. The conductor cuts the flux lines at an angle, producing about 70% of the maximum voltage. But negative. Sine 315 degrees equals minus 0.707. Finally, as the conductor completes a full rotation at 360 degrees, it returns to the same position as 0 degrees and 180 degrees. Here, the motion of the conductor is again parallel to the magnetic field lines. So no flux is cut. And the voltage becomes 0 once more. So now we understand why AC voltage is always shown as a sine wave. It's not just a random choice, it's the natural outcome of how a conductor rotates inside a magnetic field. At every angle of rotation, the voltage generated perfectly matches the values of the sine function. From 0 at 0 degrees, to maximum at 90 degrees, back to 0 at 180, and into the negative side as the rotation continues. This beautiful pattern is the direct result of Faraday's law of electromagnetic induction, proving that nature itself follows the rhythm of the sine wave.